Hello everyone, currently I'm taking a challenge on programming the game of Go. Recently, I have implemented the algorithm being described within this article, which is the Byte magazine from April 1981, the article by Jonathan K. Millen, Programming the Game of Go. So it describes the algorithm of how one can create a simple Go playing program. So I had a couple of implementations in Python, and I did rule implementation in C as well. Now I decided to go a bit further. So now I want to recreate the experience the author went through and try to program this in 6502 assembly language for the unexpanded King1, just like the author of the original program did back in the day. Another challenge is that I'm not using any assembler. I'm assembling 6502 mnemonics to opcodes by hand, and that's a very interesting kind of thing. And also, I don't have a particular guidance to what's how to do this, so I need to guess many things. And one of the challenges I've encountered already is the off-board edges detection. So how do we detect off-board squares? And we already have a few hints from the article itself, although the article itself does not particularly explain how the off-board detection is done. Still, based on those hints we can find there, I think we can recreate the original way how this was done. At the very least, my assumption on how this was done. So let's read through this. So our 15 by 15 board was used because it was convenient for addressing reasons to represent it internally within a single 256 byte page. So in 6502 based systems, there is a page called zero page. The address for this is from 0000 to 0100. The first 256 bytes, it takes less bytes for instructions to reference that memory. So it's very convenient usually. Also, on unexpanded key 1, you simply cannot allow yourself to use other memory page than zero page for storing data, because you just run out of bytes very quickly. You won't have enough space for the actual program, so all the space would be occupied by the data structures, which is not good. So it's absolutely essential to use zero pages to store some variables than data structures. So then we read the following. So we're using 1 byte per point. Although there would be a room for 16 by 16 boards, and this is very important. So this gives us the hint. A Go board ought to have a center point. So we don't use 16 by 16 because it does not have the center point. So we use 15 by 15 instead. So rows and columns were numbered from 1 to 5, etc., etc. So this little paragraph already gives us a very interesting idea, and we can make some considerations in regards to how on earth are we supposed to be representing the off-board squares, or how do we supposed to detect the off-board squares? I just want to share my thoughts with you guys, so let's have a look. So here we have a 15 by 15 hex dump. Let's say so this is the address 0000, and this is the address 0000 plus 15 multiplied by 15. Anyway, let's take the calculator and start calculating. So if we have 15 by 15 board, then this would be like 15 multiplied by 15. So we perfectly fit the 256 bytes, but usually, normally, like from just programming backgrounds perspective, we know that we usually need some off-board squares to wrap around the board, so that if we are on the edge and trying to go right, up, down, or left, that we hit the off-board square, and we know that we no longer iterate this direction. But if we add these off-board squares to the 15 by 15 board, it would be like board width plus 2 and board height plus 2. So 15 by 15 turns into essentially 17 by 17. And suddenly, it turns out that 289 is definitely more than 256. So this simply does not fit a single zero page. So this cannot be the approach. And again, another hint. So author said that he can do 16 by 16 board. And this is exactly 256. And if he said that he could implement the board of 16 by 16, and this exactly fits the zero page. This means that the mechanism for handling the off-board squares would be any but having these edges, like additional memory being occupied to represent edges. Because in this case, if we do 16 by 16 and we want to enclose them with some off-board squares, this would be 16 plus 2, 18 by 18. And this would be 324. It's definitely greater than 256. So this cannot be the way to go. So let's, again, like, this already should be self-explanatory why this is not the way to go. But I want to go a bit further with these explanations because it wasn't really that clear for me, and I wanted to make 100% sure that this approach, like in here, that it was not conceded. So let me show you some other considerations. For instance, we have the 15 by 15 board enclosed within the off-board squares. If this was a Python program or a C program, this is not a problem because in high-level languages we don't care about memory paging. So absolutely don't care about this. Not so when we write a program in 6502 assembly. Anyway, let's get rid of this, and we essentially can simplify this to this one. So how is this different? We still have the 15 by 15, but we only use one edge here, because essentially when we go from this square to the left, we encounter off-board anyway. In chess, we cannot do this because in chess, a piece, say it's here, knight can jump, say, to here. So pieces are moving in chess. In Go, stones are not moving. So because of this, it's enough to have a single edge here. So let's say we're over in here, and let's say we do go to the left. So we would simply encounter this one, and this is off board, and we are fine. Similar with this. So say we are, let's say here, we do plus 15 plus 1, so plus 16. So the next index row plus 1 essentially. So we hit the off board. And even if we try to go upwards, assuming the nature of how arithmetics is done in 6502, this would be like the carry flag would be set because we hit the negative value, and the values would be wrapping around. So essentially, for this particular square, if we want to say for this square row minus 1, so what would be this square? So the index of this square would be exactly the same as this one, with the only difference that the negative flag would be set, and I guess the carry flag would be set as well. I'm not sure, but definitely, well, at least the negative flag would be set here. So it's not a big deal to deal with off-board squares above the first line. So they essentially would be having the values like in here. So if we try to reference board index by this square minus 16, we essentially would be referencing this particular square, and we know this is off board. And interestingly, with this approach, we have 16 by 16, which is exactly the case. So this would be like enough to represent the off-board squares. But the problem is that in Kim random access memory, the Kim ROM itself is using addresses 00EF, 00F0, 00F1, F2, and F3 to dump the program counter and the registers and the stack pointer. So it's used by the operating system. And well, potentially, probably we could override those values. It's not a big deal. It's only used during debugging after hitting the break statement, but it's not really that great. And another proof here is that, let's say, if we have the 16 by 16 board, then even this approach is not going to work because, again, we just move beyond the 0 page. And to address off-board squares, we need an absolutely different addressing mode. Like instead of 0 page addressing, we need absolute addressing. So this cannot be the case, and this cannot clarify as we have room for 16 by 16. Which brings me to the conclusion that the way how the off-board square detection is done is not relying on having the specific values being initialized in memory to a certain value that does represent the off-board square. So this means that somehow the off-board squares should be calculated, defined, and figured out only based on the square index. So that's the core thought. So I have a few sketches here, some 6502 assembly codes with which was carefully hand assembled to 6502 machine codes that I've done here. And interestingly, with this code, we can achieve the desired functionality. So I will probably now just close this one. I don't need this anymore. And I would also like to go to my Q1 emulator here. Going to address 200 hexadecimal, so it's crystal clear, nothing there so far. And I want to open my nodes here. So let's kickstart with just entering a simple program that prints all the square indices, starting with 0, 0 and ending up with EE, and well, essentially not the EE, the FF. So we'll print all the indices within the single 0 page, 256, and then we'll see those that we need essentially to skip. This would be easier in terms of visual representation. So it's really much easier to show rather than to explain. So let's go. So I will now enter this program. By the time entering the opcode, I would be trying to explain what's happening. So the first thing to do, we want to initialize the X register with 0, and the X register is going to be serving as the counter to loop over board squares. So I say A200. We now initialize the X register with the immediate value of 0. Then I do TXA, no. Then I do TXA is 8A. So I transfer the value of the X register to the accumulator, to the A register. Okay, then I want to print whatever we have there. And then we want to print the space. Okay, so the next is, so 20 is jump to subroutine. Remember the little endian order. Okay, I mess up again. Yes, here 20, 3B, 1E, 29E, 1E. So this is the little endian order. So in assembly, we do jump to subroutine located at 1E, 3B, but in memory, this is represented like vice versa. The bytes are swapped. So first we start with the least significant byte, this one, and then we go to the most significant byte. So that's the specifics of the 6502 addressing. Okay, and finally, we want to increment the X to increment the counter. So we do E8, and then we do a loop. So if X register is not equal to 0, so it would be wrapping around. It would be 0, 1, 2, 3, 4, and then it would be FF, and then it would, after it's FF, after we do the increment, it would be 0 again. And in this case, the 0 flag would be set. So branch not equals means that unless the 0 flag has been set, that we want to continue the loop. Once the 0 flag is set, we no longer want to loop. So 0 flag is not set, we're looping. 0 flag is set, this means that we just wrapped around the 256 values that we were interested in, so we no longer need to loop anymore. Okay, so branch not equals is D0, and this value is calculated manually, so this is the relative offset from here to here, which means that we want to jump 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bytes behind. It's a separate topic how to calculate this, but yeah, let's drop this for now, and otherwise this video would last forever. Okay, so let's quickly check this out. So loading 0 to accumulator immediate value. Accumulator goes, loading 0 immediate value of 0 to X register. Then the value of X register goes to accumulator. Then we print the accumulator as byte of 2 digits. That's the KMROM routine. Then we print the space, then we increment the counter, the X register gets incremented, and until we, what is this? Oh, this is just another function. So we increment the counter, and until we have the 0 flag not being set to 0, we continue to loop. So I do 0 to 0, 0 and go. Okay, I forgot to set the relative offset. Okay, now we have all the values we are going through. So 0, 0, okay, 0, 1, so all this okay, and then this one is off board because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We have the 15 by 15 board, and this is 16, so we don't need this one. Okay, then we go another 15, and again we have this one which is off board. Then we go further on, and then we have this one off board. So what's similar within these values? It has f in the byte. So the rightmost nibble of the byte is f here and here. Okay, and then we have the row that starts with f. So all this row is entirely off board, which gives us an idea that if we have f in the left nibble of the byte, or if we have f in the right nibble of the byte, this means that the square is off board. So this is quite a naive approach, and this is not very efficient in terms of using memory, and this would bring us to some duplications. But still, I want to show you how this works. So let me just reload my Q1 emulator here. And now we go for a second program. So the second program is quite similar, but it has some significant changes. So we start with loading the immediate value of 0 to the X register, then the same 8A. We transfer this value to the A register. And now we do the AND operation. So whatever we have in the A register, currently that's the square index. So we do AND with a value of 0F. So we mask the rightful bits of the byte. And to do this, I do 29, 0F is the value to bitwise AND with. And then we compare. If this value equals exactly to 0F, which is 15, we know that the rightmost 4 bits of this byte is equal to F, and this is the off-board square, so we don't want to deal with it, and we want to skip to the next square. So C9 is compare the immediate value of 0F, okay, and if this value equals exactly to 15, the 0 flag would be set. So we do branch equals, so F0 is the opcode for branch equals, and 0E is the relative offset that brings the program counter pointing to this byte to be executed next. So F0, 0E, okay? Now we do exactly the same thing, but with the first, with the leftmost 4 bits. But first we need to make sure that our source data is proper again, is correct again. So again, we want to say transfer the value of X to the A register, because after bitwise ending, the value of the X register has been changed after masking. So we do again 8A. So now A register again has the value, which is the square index. And then we do again bitwise end, this time with F0. So we mask the leftmost 4 bits. Then we compare the value with F0, which means if this is true, then this means that the first 4 bits, the leftmost 4 bits within the square index, contain F, and this means that the row goes off board. So here we ask if column is off board, and here we ask if row is off board. Okay, so the next one is we want to skip if F0 and 07 want to skip. Okay, and then again we need to restore the value, because otherwise we would print some gibberish, because after we have altered the value of the accumulator with its AND, is no longer equal to the square index. So we do 8A, okay, and then we do our print routine. So 20, 3B, 1E, 20, 9E, 1E. And then again, we just want to do E8, increment the counter, the X register, and then we want loop back in case if we did not loop over all of the 256 bytes. Now hold my breath and try to run this stuff and see if this works. So we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And then we don't have the 16, so yeah, I've already deleted that scheme for the board. But anyway, so after this, so this is the board edge. So this is the 15th square, the 15th byte in the first row. So the next one is off board. So we skip it. So we just did manage to detect the off board. So we skip it. So what do we do on off-board detection? We want to take some action. In case of just printing these squares, we just want to skip, but we can do any other action if needed. And then we start from the second row. So second row goes up to 1C, 1E goes up to in here. Second row goes like this. And then again, there is no 1F, so we just go the next row ends up with 2E and no 2F, and so on and so on. And the very last one is EE. So all that starts like F0, F1, etc. So this last row, which is entirely off board, we don't take that into account because that's off board. So this is how we did manage to deal with off-board squares. However, this is not the most efficient approach of dealing with it. So I just want to show you another tiny little optimization I came up with, which is only 3 bytes smaller than this one, but it just looks much better and I like it more. And I do assume that this is something looks like what could be used by Jonathan K. Millen in his original implementation. I might be horribly wrong though, but that's my assumption. So the idea behind the optimization is the following. We don't particularly need to mask the leftmost 4 bits, because essentially we can just compare with this constant value EF. We're not comparing with F0 because in that case we do rely on the carry flag being set and the specifics of how the carry flag has been set in 6502. So the value should be greater or equals. In this case, the carry would be set. So Did I say this properly? Let me just quickly check this out. If the value in the accumulator, if the value in the accumulator is equal or greater than the compare value, the carry flag will be set. Yeah, this is what I wanted to say. So the idea is that this row, so we have like row 1, 2, 3, 4, 5, and row 15, and then row 16. So we don't have to particularly mask the value of the row 16 to figure out if the first nibble is f or not. We can just run it by the value. So the value of indices starting from f0 and to ff, they would be greater than, oh my goodness, than ef. Yeah, that would be greater than ef. So those values that are greater than ef, those values greater than ef are f0, f1, etc., and up to ff. We're not interested in this. So if we figure out that the value in the A register, in the accumulator, is essentially greater than ef, or greater or equals than f0 and up to ff. In this case, we just skip. So this is the shorter way how we can deal with this. The rest is the same. We still need to mask the right 4 bits, to know if we need to skip them or not. So let's quickly put this code in. So again, we have a2 0 0 x equals to 0. Transferring this value to the accumulator. Then we instantly do compare. So C9 compare with EF, and if B0, if the carry flag is set, we jump to skip. I did not mention the skip in this last. So here the skip is okay. So this jump, oh my goodness, where is this? Yeah. So this jump brings us in here. Okay. So B0, 0D. And then we do what we did previously. So comparing, bitwise ending with the 0F, comparing with the 0F, and 0, 0, 7, jump into skip if it's equal to 15, if it's off board. And then we do restore the value in the accumulator. Then we do the print stuff, 3b, 1e, 20, 9e, 1e. Then we do increment the x register, and we loop back until we do not wrap around. So let's try to see. Okay, something has gone wrong. So A2 0 0, A8 C9 EF B0 0D 29 0F C9 0F F0 07 8A 23B 1E 20 9E 1E E8. Oh, not 0D, D0. Okay, D0 and EB. Yeah, one single typo leads to disaster. Okay, so this is exactly the same output as we had before. So it starts with the 15th column, not going further. So then it goes to the second row. Then it goes to the third row and so on. Then it skips the very last row, which also goes off board. So this is my assumption how we can check for the off-board squares without using any particular off-board memory cells to have specific values there, marking the off-board square, but just relying on the bare square index. That's it from my side, guys. Thanks for watching, and I'll see you next video. Until then, and cheers.